Not all sounds at the same decibel level seem equally loud. This video will show you how to use the equal loudness curve chart to determine the perceived loudness of a frequency at a given sound pressure level. By the end, you'll be able to summarize how a sound's frequency impacts its perceived loudness. This is a chart of equal loudness contours. It's based on experiments conducted in 1933 by Harvey Fletcher and Wilden Munson. Fletcher and Munson set out to determine how loud sounds of different frequencies had to actually be in order for people to perceive them as the same volume. These curves reflect the results of those experiments. Different frequencies don't sound equally loud. How different they sound depends on how loud they actually are. Let's talk about how to read this chart. On the x-axis, you see frequency in hertz. Remember, the higher a sound's frequency, the higher its pitch. The frequency range of this chart is from 20 Hz to 20,000 Hz, the average range of frequencies people can hear. On the y-axis, you see sound pressure level in decibels. Remember, sound pressure correlates to the amplitude of the sound waves. This chart ranges from 0 to 130 decibels, the amplitude you perceive as silent, to the amplitude that will instantly hurt your ears. The dotted line on the bottom represents the threshold of audibility, as in, how loud does the frequency have to be in order for a person to notice the sound at all? This is a sound at 1 kHz. Say you wanted to know how loud a sound had to be at 1 kHz in order to be audible. First, you'd find 1 kHz on the x-axis of the chart and follow that line up to the curve for the threshold of audibility. Once you hit the curve, you'd look over to the y-axis to see the sound pressure level. And you'd find that a 1 kHz tone is audible at about 3 decibels. No surprise there, the decibel is based on a 1K tone. If 0 decibels at 1 kHz is silence, and humans need to hear a 3 decibel change in order to perceive a change in sound pressure, then it's no surprise that a 1K sound first becomes noticeable at about 3 decibels of sound pressure. What about a sound with a lower pitch though? This is a sound at 200 Hz. Say you wanted to know how loud a 200 Hz tone had to be before you could hear it. You'd find 200 Hz on the x-axis and follow it up to the curve, find where this part of the curve meets the y-axis, and you discovered that a 200 Hz sound has to be at least 12 decibels before you can hear it. Lower pitched sounds seem quieter, and at very low volume they have to be a lot louder to be heard. This is why people boost the bass when they're listening to music. Those sounds are actually harder to hear. As you go even lower, the difference gets more extreme. Say you wanted to know how loud a 40 Hz tone had to be in order to be audible. I'm not going to play a 40 Hz tone for you because if you're listening to this through your computer, your equipment probably won't be able to reproduce it. Find 40 Hz on the x-axis and follow it up to the audibility curve. Find where that part of the curve falls on the y-axis. And you discover that a 40 Hz sound has to be 50 decibels before you can hear it. But what about higher pitched sounds? This is a sound at 4 kHz. Look at where 4 kHz meets the audibility curve. Follow that over to the y-axis, and you can see that a high-pitched tone like this is audible below 0 decibels, at around -2 decibels. That means you can hear a high-pitched tone like this with less than 20 micropascals of pressure. Notice that as the frequency climbs even higher though, the curve swings up again. Really high-pitched sounds are hard to hear. Think of a dog whistle. To a dog, it seems loud, but to a person, it's either silent or barely audible. As perceived sound pressure changes, the shape of the curve changes too. Let's jump up to the curve for 70 decibels. How loud does a 1K tone have to be in order to sound like it's 70 decibels? 70 decibels, of course. Remember, 1 kHz is the reference for the decibel. What about a 40 Hz tone? 90 decibels, a lot more amplitude than a 1K tone. Still, it's not as big of a difference as there was on the audibility curve. Looking at a higher pitch, a 4K tone. You can see that it doesn't have to be as loud. A 4K tone at only 61 decibels of sound pressure seems as loud as a 1K tone with 70 decibels of sound pressure. Jump up to the 100 decibel curve. The pattern is the same, but the changes are less drastic. 1 kHz sounds like 100 decibels at 100 decibels because that's the reference value. In order for a 40 Hz tone to sound as loud as a 100 decibel 1K tone, you would need at least 113 decibels of sound pressure. And for a 4K tone to sound as loud as a 100 decibel 1K tone, it would only have to be about 88 decibels. When you look at all three of these curves at the same time, they seem to be pretty much the same shape. Why do you need different curves for different perceived sound pressures? Well, take away the chart for a moment, and lay the curves one on top of the other so that they line up at the 1 kHz point. Now you can see that they all deviate from that point in slightly different ways. Also, the green line representing 100 decibels deviates a lot less than the red line representing audibility, or even the blue line representing 70 decibels. The curves flatten out at higher sound pressure levels. Even at varying frequencies, loud sounds seem loud. In summary, frequency impacts how loud one sound seems relative to another. Low-pitched sounds don't seem as loud as mid-range or moderately high-pitched sounds, even if they are actually the same amplitude. At higher sound pressures, though, frequency makes less of a difference in perception. The equal loudness contours tell you how loud a sound of a given frequency must actually be in order for it to seem as loud as a 1K tone of a given decibel level. Thanks for watching Equal Loudness Contours.